this morning to have Emil Martinec with us. He gets me here for a while and he's staying for a while more. He'll be telling us about the polar wind.
Okay, thank you to Nick and Josef for hosting me yet again on my annual pilgrimage to Paris. And so what I'd like to describe today is some work that I did over the last few months. So let's just begin. Oh yes, and I decided to do things slightly differently because if I use my iPad, people will be, on Zoom will be able to see what I'm pointing at, and everything seems to look reasonably decent. So, so we've been thinking about this Penrose diagram for quite a while now, trying to figure out what's wrong with it, and you know, what are the basic ingredients we need to patch it up? We want something that stores information inside a black hole, and then releases that information in some kind of quantum coherent way. And so far, you know, we're not there yet. What we have is sort of one aspect of the problem, at least the beginnings of one aspect of the problem in thinking about black holes in string theory, that is the information storage problem. At least we have some robust accounting for near extremal microstates that could serve as a storage device for quantum information. But we still don't have a bulk picture of what's going on at the horizon and beyond. And so what I'd like to describe today is a family of situations where we can begin to address what's going on. And this family of situations I'd like to think about are various brain systems wrapped on tori. And the canonical example, much studied in the context of gauge gravity duality, is D-branes wrapped on tori. So let's just think for a moment about a DP brane wrapped on a p-dimensional torus. The family of solutions that are sourced by the branes was described by Horowitz and Strominger quite a while ago. So, well, the DP branes source some antisymmetric tensor gauge field in type 2 supergravity, whose configuration is described by some harmonic function, which is, you know, constant plus 1 over the distance from the branes to some power with a coefficient given by the brane charge. In general, there's a dilaton, non-trivial dilaton is sourced as well. And the branes then back react on the geometry in a way which, if you get near the source, this piece of the harmonic function starts blowing up, which means the proper size of the directions along the brane starts shrinking, and the proper size of the direction transfers to the branes feels some pressure from the antisymmetric tensor flux and tries to expand. And if we make the system non-extremal, then there's some other harmonic function that describes the non-extremality, makes a horizon at some radius r0. And we'll be interested in the decoupling limit of this situation, which just means we drop the constant in this harmonic function so that the warping is some kind of power law, depending on the dimensionalities involved. Okay, and so this is a tailor-made for gauge gravity duality, because gauge gravity duality is precisely the situation where you zoom in on the near source structure of the branes and take a low energy limit, which is just going to large redshift in the geometry. And so in that limit, we're in a situation of gauge gravity duality. The dynamics on the branes just becomes the corresponding gauge theory on a toroidal spatial domain. And so, for instance, for p equals 3, we have n equals 4 Yang-Mills living on a 3 torus. And more generally, you just have maximally supersymmetric Yang-Mills on the appropriate dimension torus, and that is dual to this warp geometry in this decoupling limit. Okay. But thinking about what's going on sort of locally in the geometry, because there is this radially dependent dilaton, if you're not in the ADS3 example where the dilaton is, so key factor is that that harmonic function is raised to a power 3 minus p. So for D3 branes, the dilaton is constant, as you would expect for maximally supersymmetric Yang-Mills. That means that the Yang-Mills coupling doesn't change with the radius. For the more general p-brane geometries, there is some radially dependent dilaton. That radially dependent dilaton is just coding the flow with energy in the usual UV-IR correspondence of gauge gravity duality. Is just telling you how the gauge coupling is flowing with energy. But in the dual geometry, the dilaton is telling you, say, for instance, in a type 2a situation, what is the size, proper size of the 11th dimension. So, so if I think about, say, D0 branes, they have some dilaton which is weak in the UV and is gradually growing in the IR. And so at some radius in the geometry, the size of that extra dimension becomes the Planck length or bigger, and you start thinking of it as being an 11th dimension of space. And so if you then are thinking about these black geometries, some non-extremal collection of D branes, then if the non-extremality was really tiny, what you should be thinking about is a D0 branes describe momentum in the charge they carry is the momentum in the 11th dimension. So you're looking at some kind of object which is sitting here running around in the 11th dimension and is boosted, because that's what D0 brane charge is. If, on the other hand, the non-extremality is bigger, the horizon radius is sitting out here, and you should think of it as a collection of black D0 branes in type 2a string theory. So depending on sort of where you are in the parameter space, you want to think of the object you're describing in different ways. And the thing that we're going to be interested in is the fact that we can take this harmonic function and we can that describes the collection of branes, and we can split it apart into multi-center harmonic function. And so because we're looking at D branes on tori, there's a Coulomb branch to the gauge theory. So the dual description of this is just taking collections, sub-collections of branes and separating them apart in space. Okay. In the M theory regime, this is just describing collections of objects which are separated in space and moving around in 11 dimensions. Okay, and so the Banks, Fischler, Schenker, Susskind matrix model is this particular limit, low energy limit of a collection of D0 branes, and the separated D0 charge are just describing different objects with different amounts of boost in the 11th dimension. Okay. But there's definitely, even in the decoupling limit, there is this Coulomb branch, and we're going to make use of that in what follows. Okay. Now, we're used to thinking of in gauge gravity duality of, what are the observables? Okay. The usual observables we think of in maximally supersymmetric Yang-Mills theory are single trace operators. And single trace operators are dual to various modes of the supergravity fields in the bulk. And so, but all of those supergravity modes in all of these geometries have some wave functions which are decaying as you go towards the boundary, spatial boundary of the geometry. So if we're talking about D branes for p equals 3, it's the standard ADS 5 cross S5, toroidally compact. You take the Poincare section of ADS 5. Toroidally compactify it, and that's your geometry, and everything you know about in ADS5 duality is, in terms of single trace operators, is just describing some particular Fourier modes of supergravity in the bulk. So all those wave functions decay towards the boundary. They don't describe something, if you're thinking about a black object which is trying to Hawking radiate, all that Hawking radiation is trapped in ADS. It never gets out, it tails off, and whatever Hawking quanta you have, get out somewhere in the bulk, and then they fall back into the black hole. But in this situation, because there's a Coulomb branch, there's also the possibility that you radiate part of the charge that the background branes are carrying. So if we have this lump of DP brane sitting in the middle of some warped geometry, there's some tiny but finite probability that one of the DP branes that's in the bound state escapes as a Hawking quantum. Okay, and so what we're going to be interested in describing in what follows is what is the amplitude for that process of a DP brane radiating one of its members onto the Coulomb branch that then escapes the system. Okay, so there's always the possibility of turning that off. So you can always lift the Coulomb branch in some way. So for instance, if we're having this D0 brane system, there's a well-known deformation of the quantum mechanics of D0 branes called the BMN deformation, which puts a potential which keeps the D0 branes from escaping to infinity. I'm always going to be wanting to work in a situation where I'm not going to do that. So the quantum mechanics has this sort of flat direction in its configuration space where stuff can leak out. And so the details of the sort of phase diagram of things that you can describe depends on which value of P you're talking about. For D0 branes, there's just what's the energy of the system or the entropy of the ensemble. And as I was describing before, if you're in a low entropy, low energy situation, you're describing 11 to be black holes that are boosted in the 11th dimension. And for somewhat higher energy, you're describing D0 branes. If you make the thing too energetic, then the UV dilaton becomes weak enough that you're describing some perturbative collection of D0 branes, highly thermally excited rather than something that has a geometric dual. And as I say, for different values of P, you have different things going on. For P equals 1, you have something that's the Verlinde is described as matrix string theory in some corner of parameter space. The P equals 3. Oh yes, for P bigger than 0, there are two directions. There's increasing energy, but then there's also changing the gauge coupling. And so depending on which direction you go, you get different characteristic behaviors of the system. Something that's has been and will be quite a focus this week is the D1, D5 system, which is just another variant of D branes wrapped on tori. And so just to set some later notation, we'll be thinking of the D5 branes as being wrapped on a 5 torus, of which we single out the particular circle of that 5 torus that's also wrapped by the D1 branes. And to set some notation, we'll call that direction Y. The rest of the directions comprise some T4. And a variant of that D1, D5 system that I would like to also focus on is where we consider the S-dual system, where instead of having 1 branes and 5 branes, D branes, we have NS5 branes and fundamental strings. So that's just the S-dual of this particular situation. And the reason I would like to focus on that is that there's a very well-developed worldsheet formalism for describing string theory in the vicinity of NS5 branes that was developed by Givon, Kudasov, and Seiberg with important additional work by Maldacen and Aguri. And so the situation we'll consider is some number of NS5 branes, again, wrapping the T5, fundamental strings that are also wrapping this so-called Y circle. And the decoupling limit for this situation in the presence of these NS fluxes is taking the string coupling to 0 and the radius of this Y circle to infinity. So taking the radius of the Y circle to, so first of all, taking G string to 0 decouples the flat space region transverse to the 5 branes and focuses on the 5 brane throat. And then taking Ry to infinity is the limit in which that 5 brane throat becomes an ADS3. And so the ADS3 in the geometry is basically made up of the radial direction away from the branes, time, and this Y circle is the azimuthal direction of ADS3. And once again, this system has a Coulomb, what you might call a Coulomb branch, namely that a fundamental string that's wrapping this Y circle can get out to spatial infinity in ADS at finite cost in energy. You might say, why is that? Because if the string is way out here near the boundary of ADS, isn't it enormous and doesn't that cost you a huge amount of energy? The answer is no, because this ADS3 is threaded with Newton-Schwarz B-flux. And the Newton-Schwarz B-flux, oops, is some field strength, some h rho tau rho t y. And then if I have a world sheet that is wrapping the y direction and going in the time direction, that exerts a force in the radial direction. Okay, and so the value of the h field strength that makes the ADS3 is precisely tuned so that this radial force of what you might call the Lorentz force, the analog of the Lorentz force for strings, precisely balances the tension of the string. And so the balance is such that it costs you a finite amount of energy to get out to infinity. It's mutually BPS, absolutely. So this is just the near horizon limit of some cartoon of separating strings transversely from the stack of phi branes string bound state. And this is an argument that that picture doesn't decouple as you take the decoupling limit. It's still finite energy even after you've scaled all the energies to the decoupling limit. Okay, so the thing that we're now going to consider is what is Hawking radiation? These branes are wrapping the tori, depending on which of these situations you have. So let me think of the torus direction as being this direction in some kind of Penrose diagram. And so there's a horizon. There's a radial direction out to the boundary of my space. And so, if these were particles, there would be a particle Hawking process, right? Which is I nucleate a particle-antiparticle pair near the horizon. One of the antiparticle members stays behind the horizon and decreases the mass of the black hole because it's in a negative energy state. And the particle member of the pair runs out to infinity. So we're just going to consider the brane analog of that process, where we nucleate a brane-anti-brane pair with the brane wrapping the horizon. Because the horizon is some 3 torus or p torus, or in the case of the 1 brane 5 brane system, it's this Y circle. And so we're going to pair create those branes, and we're going to have one member of the brane pair go out to infinity, and the other one being the corresponding anti-brane.
Are you going to use any of the dependence on the circles, or is it? In other words, can I not think of this just as a particle on an ADS2 and it's the Hawking process?
If I'm looking at a rotating BTZ black hole with an ADS2 limit, then yes, you're free to use that intuition. Absolutely. In fact, that was the way I sort of first approached this, was to think about that limit. And yes, isn't my string just a particle in ADS2? And so shouldn't it be doing the same thing that other charged particles ADS2 can do? So yes, but this is much more general. I don't need to be in the ADS, near extremal limit of my black hole. It can be a non-spinning BTZ. Okay. And furthermore, it also describes all these other situations of wrapped P branes wrapped on tori. Okay. So what we're going to do is repeat a style of calculation that I guess originally goes back to Hartle and Hawking, who thought of the pair creation process as some WKB approximation to the 2-point function of the whatever quantum field you're looking at whose quanta are being Hawking radiated. You can think of the pair creation process in terms of some calculation of the 2-point function in the black hole geometry, and then making a WKB approximation to that 2-point function, which turns out to be very accurate in the vicinity of the horizon, where everything gets highly blue shifted and the WKB approximation gets better and better. Okay, and so what we're going to do is look at some first quantized formalism for particles or strings or branes that are doing this. And so we're going to just write down the world volume action on the brane. and then think of the amplitude for Hawking creation as some kind of WKB tunneling amplitude. So the way this way of thinking about things goes back to some work of Krauss and Parikh and Wilczek back in the 90s, where you say, okay, I have a horizon. Let's think about, say, a vacuum fluctuation just inside or just outside the horizon. And we want one member of the virtual pair to tunnel out across the horizon and escape. Or you can think of pair creation of a vacuum fluctuation just outside the horizon, where the antiparticle member tunnels through the horizon to the inside. It doesn't really matter all that much. And so that tunneling amplitude is just going to be an imaginary part to the classical action of the trajectory of the brane or particle or whatever you're talking about. And so we'll be interested in the world line action for the brane. It'll have some kinetic energy, some rest mass, coupling to whatever antisymmetric tensor field couples to the brane, which we can dimensionally reduce to the center of mass. Okay, and the metric that the ambient geometry being felt by the brane is just going to be the appropriate black brane geometry in some suitable coordinate system. And I don't really care about what coordinate system we're using, so long as it's not there's no coordinate singularity at the horizon.
What are you doing about the angular momentum when you Euclideanize?
I'm not Euclideanizing.
You're
I will
not?
nowhere here Euclideanize.
Okay.
We'll see in a minute what I need to do. So I just need some non-singular coordinate system. Krauss, Parikh, and Wilczek use some coordinate system called Panelovic-Gullstrand coordinates. They're similar in some respects to ingoing Eddington-Finkelstein, which you can also do the calculation in those coordinates. As I say, it doesn't really matter deeply what the coordinate system as long as it's non-singular. There's no.
At this point, it's extreme one near extreme one, far from extreme one.
I've taken the decoupling limit, so it's just some black geometry, well, ADS or anyway, any black D-brane geometry in the limit where I drop the ones from the harmonic functions. Okay. So the next step in the analysis is to go from this Lagrangian worldline formalism to Hamiltonian path integral. So introduce the momenta that are conjugate to some momenta p mu, which are variations of the action with respect to x dot. And so after doing that, you just have some PDX plus the Hamiltonian, which, because the worldline formalism doesn't depend on what coordinates you use on the world volume, there's some Hamiltonian constraint reflecting that fact. And so the next thing to do is to solve the Hamiltonian constraint for the radial conjugate, momentum conjugate to the radius. And when you do that and you focus near the horizon, what you find in any of these coordinate systems is that this radial momentum of the particle has some universal form. That is, there's a pole in the canonical momentum for the radial momentum of the brane. And then the residue of that pole, I'm still in Lorentz signature, okay? So the residue of that pole is just geometrical properties of the horizon. So first of all, the particle has various conserved quantum numbers that or the brane, I should say, the wrapped brane is various conserved quantum numbers that it's carrying. So it can have some energy. My geometry, if I'm working in some nice stationary coordinates, the geometry is independent of all sorts of, there's various sorts of killing coordinates. So there's the time, there's the angular coordinates along the horizon, et cetera. So, there are angular velocities of the horizon. If the brane carries some charge, so there's the value of the gauge potential at the horizon. Okay, and then there are all the conserved charges carried by the brane that are conjugate to, that couple to those various potentials, which are, the energy, the angular momentum, the charge, et cetera. And then there's the surface gravity of the horizon. Okay, so this radial momentum, which is the thing that's doing all of the interesting work in this trajectory, tunneling trajectory, is expressed very nicely in terms of some geometrical properties of the horizon plus the conserved charges carried by the escaping brane. And then the next step suggested by the analysis of Wilczek and collaborators is to deal with this pole, right? Because if the trajectory is trying to get from inside the horizon to outside the horizon, then at some point it has to cross the horizon and it hits this pole. So the way we avoid, usually one thinks about this by, continuing everything to Euclidean space, dealing with some kind of Euclidean geometry and trying to do the calculation there. Wilczek and friends said, I just need to deal with this pole. I just need to get inside the horizon to outside the horizon somehow. And so let me just deform the trajectory, not that you deform the geometry, but deform the trajectory into the complex coordinate plane for the radius. And so they just say, okay, let me deform the radial integration slightly out into the complex plane and go around this pole and get from inside the horizon to outside the horizon that way. And so, there's an appropriate direction to go around so that the amplitude is damped rather than blowing up. And so they just do that. Okay. But in the process, you pick up an imaginary part, which is just concentrated at the infinitesimal vicinity of the horizon where you deform the contour. And so again, the imaginary part of the classical action for the escaping brane is just dependent on the horizon properties of the trajectory near the horizon. So it's completely universal and geometrical. Okay, but it depends on the charges that are carried by the brane. But of course, the charges being carried by the brane are just being extracted from the black object that you started with. So it subtracts from the energy, it subtracts from the angular momentum, subtracts from the d-brane charge, and so on. And so I can replace those conserved quantum numbers being carried by the brane by the opposite amount of the reduction of the corresponding quantities of the remaining black hole left behind. And then what you recognize here by the first law is that this is just the change in the entropy of the black hole left behind with a factor of 2, which will be crucial. Because this is the tunneling amplitude, if I want the tunneling probability, I just square this. And so then we have a universal probability for a black brane with a Coulomb branch radiating charge out onto its Coulomb branch, which is universally expressed in terms of the change in the entropy of the black hole during the process. Now, Wilczek and collaborators were interested in this because they were interested in the regime where the charges being radiated are some finite fraction of the mass and charge and angular momentum of the black hole. And so shouldn't there be corrections to thermodynamics when we get into that regime? And so they were interested in estimating what those corrections were. Yes?
There's a question about the phase space.
I mean, this calculation doesn't care how much phase space you have before the tunneling, how much phase space you have after the tunneling. So this is just for a single brane to tunnel in and out. It doesn't calculate the phase space.
Well, we'll get to the phase space interpretation of this in a minute. Okay. As long as we're on the subject, let me go through some details of the ADS3 example for people who are aficionados of ADS3 CFT2. So here, as I said, there's a worldsheet formalism, which comes about because ADS, so the BTZ black hole is just some quotient of ADS3, and ADS3 is a group manifold. So the worldsheet just says, oh, Wess-Zumino-Witten models, I love it. And says, I can describe strings in the presence of a BTZ black hole. And so there's been literature that's been percolating over the last 25 years, developing the formalism for describing perturbative strings in the presence of BTZ black holes, which just is some elaboration of SL2R Westernino-Witten theory. In particular, the BTZ geometry is some quotient of the group manifold by some left and right hyperbolic discrete transformations in SL2R. Where the discrete identification of the group manifold that's being done is determined in terms of the inner and outer horizon radii of the BTZ black hole. And so you get some Penrose diagram. So this is some kind of cartoon of, on the right, of what that geometry is, where you think of having sort of the standard, the standard cylinder, ADS cylinder. Okay. And you're going to make some identification of the geometry by some discrete boost transformation that identifies the inside and the outside. And when you do that, what you find is the fundamental domain of this identification is the region between this slice and this slice. And you recognize that you're describing some geometry that now has horizons. And outer horizons and inner horizons and singularities and so on. Okay. So we're interested in describing these classical trajectories in the WKB approximation for a string in this geometry. So the first thing to think about is point-like strings. Those are just traveling various geodesics, which can be either time-like, null, or space-like, depending on what the mass parameter is in the Hamiltonian constraint. Then once you have a geodesic describing a point particle, it's very easy to get a wrapped string by using the symmetries of ADS and what's called spectral flow transformation. So transformation where you take the group element and you left and right. So first of all, I should say, the classical solutions to the equations of motion, the worldsheet equations of motion, are just that the worldsheet is traveling some trajectory which can be factorized as a product of left and right holomorphic and anti-holomorphic group elements. Actually, I think I wrote it the other way. Whoops. G of Z, G prime, or G twiddle, call it, of Z bar. Okay, so any classical solution of the equations of motion on the worldsheet has that form. And so now, if you have such a solution, in particular, if you found the solution that corresponds to one of these point-like geodesics, so here's some point-like geodesics. Here's a time-like geodesic which just sits there and oscillates in the middle of ADS, or you can have one that emerges from the singularity, comes out, pokes out of the horizon a little bit, and then falls back into the black hole. So the various trajectories like that. Take any one of these classical particle trajectory geodesics, which are just standard, integral curves of some generator of SL2R, and make the following transformation of it, multiplying it by a left and right function of Z. And what you'll notice is this is, well, so first of all, this is yet another solution of the worldsheet equations of motion. So it's another classical string trajectory. But it now has the property that if I send Z goes to Z plus 2 pi, you'll notice that this group element and this group element is just an integer power of the identification that makes the BTZ solution. So I've just taken a point-like solution and I've transformed it in such a way that it makes now some string that's wound around the identification some number of times. So that's a way of getting wound strings. And furthermore, because this is all group theory of affine SL2, the energy, the angular momentum, et cetera, of this string trajectory is completely determined by the corresponding properties of the point-like particle geodesic together with the spectral flow. And so in particular, then there's this slightly non-classical trajectory that we're interested in, which basically consists of an antiparticle trajectory just inside the horizon together with a wound string trajectory just inside the horizon, a wound string trajectory just outside the horizon, and a bit of tunneling from one to the other to describe the pair creation process. And again, the probability for that is again given by the change in the entropy of the BTZ black hole. The BTZ black hole has a well-known formula for its entropy, which is matching that of the dual CFT2. The energy and the angular momentum are determined in terms of the inner and outer horizon radii. The entropy of the black hole is just the horizon area. So one can just evaluate what is the change in the entropy of the black hole during this emission process, and you get this expression. So you recognize, for those of you who know well BTZ black holes, this is the surface gravity of the horizon, aka the temperature of the BTZ black hole. And then you have a suppression based on how much energy is being extracted by the string, how much angular momentum, and together with the winding of the string is the amount, the number of windings of the string is telling you what is the amount of string charge that's being radiated in this process. And so because the entropy of the black hole is proportional to the string winding, then there's a rather substantial suppression, basically because the, what is the entropy of the BTZ black hole? It's basically that you have this gas of strings that are dissolved in the 5 brane, and that gas of string can carry various momentum excitations. And the BTZ regime is where that gas of dissolved strings is sort of wrapping the BTZ horizon, of order this many times. And so we were trying to extract some winding, then you're sort of decreasing the volume of string available to carry momentum excitations in what you've left behind. And so every time you try to make the box that the gas of excitations is living in smaller, while keeping the energy the same, you've had to decrease the amount of, so the excitation, how do you say, the sort of typical excitations have to become shorter wavelengths because they're living in a smaller box. And so you can't have as many of them. And so you reduce the entropy of the black hole in proportion. Okay, so now comes time. Yes.
The sign of W is fixed. If you change the sign of W change that.
Yeah. So in order to have this Coulomb branch, I need the sign of the winding to be the same as the orientation of the H flux of the ambient BTZ. So you're only emitting strings with the same winding as the background. It costs you way too much energy to emit the anti-winding strings. Okay. So now comes to the fun part. So we have this answer for the probability to emit, and I'd like to interpret that in terms of microscopics. So we should think of this emission process as some kind of inclusive decay, where the final state is so the initial state is some BTZ black hole, the final state is some smaller BTZ black hole and some string outside the horizon. And the gravity calculation really doesn't know about the microscopics, so it averages over the microscopics. And so you should think of it as some kind of inclusive process where every black hole that it could possibly make, you could possibly make a transition to during this process is included in some sum over states. And then there's some square of a transition matrix element. Okay, how many states are there? So go back to your quantum field theory, right? An inclusive process is you sum over final states. So there's a sum over all possible final state black holes you could have, and then a square of some transition matrix element for each possible process, given whatever black hole you're starting with. And so, what are we finding? Well, they're of order e to the SF final states. So that explains this factor. And then the natural conclusion is that every one of these matrix elements is of order the same order, namely e to the minus s over 2. And e to the minus s over 2 of the initial black hole. And so this should remind you of the eigenstate thermalization hypothesis, where some complicated thermal chaotic system has matrix elements that are well modeled by something where you stay in the same state, and then something where you make transitions, but the amplitude for making transitions is exponentially suppressed in the entropy of the system in more or less this way. Usually it's thought of as being the entropy of the average of the two energies of the initial and final state. I'm claiming that this particular process, the natural thing that comes out is the entropy of the initial state. And then, some smooth function of the energies and some, randomization of the matrix element. And so I think the natural conclusion from the calculation is that the corresponding thing that we're calculating, that we've calculated in the last few minutes, is a transition matrix element where you start with an initial black hole and you go to some final state black hole plus a string on the outside, or particle or whatever. And that the transition matrix element for that process is just some pseudo-random matrix element, then smoothly, this sort of thing is going to contain things like gray body factors and other kind of order 1 crap that you don't really care about. And then there's this huge suppression factor coming from the entropy of the initial state, or the available number of initial states. And so the conclusion I'd like to, oh yes, and I should say, when I went through the calculation, I said, oh, there's this pole in the, I solve for the radial momentum, and there was this pole, and so on and so forth. When I'm solving the Hamiltonian constraint for the radial momentum, well, the Hamiltonian constraint's quadratic in the radial momentum, and so there are 2 solutions, and I picked the one that corresponds to the particle tunneling out. The other one corresponds to a particle or string falling through the horizon going inwards. That process, of course, is the adjoint matrix element, where I start with a black hole with a string on the outside, and I go to a somewhat bigger so I start with a smaller black hole and go to a bigger black hole, string going in. That should be, if this is the right interpretation, that should just be the adjoint matrix element. Okay, and so all I do is I reverse the roles of the initial state and the final state. So this exponential suppression now becomes an exponential suppression with the final state entropy. But now when I do my inclusive sum, the factors of e to the s cancel each other, right? That the e to the sf of the density of states of the sum is canceling against the e to the minus sf in the matrix elements, which is just the statement that falling into a black hole is not suppressed, it's order 1. And so again, this picture is modeling that, what you see from the world sheet dynamics in the appropriate way. So the lesson I draw from this is that everything that's going on is just phase space. That the probability of things happening is just governed by the fact that the black hole has this enormous internal phase space that you access when you're inside or when you're falling in. For those of you who know something called Doctor Who, which is this British sci-fi television show from decades past, the black hole is like the TARDIS. It's much bigger on the inside than it looks like from the outside. And moreover, the causal relation between what's going on the inside and what's going on the outside is also not what you thought it was. but in other words, everything here can be modeled by just saying that the black hole is like has some enormous internal phase space, and that you access it by falling in. Once you fall in, you rattle around ergodically in this phase space like any chaotic system. And your probability of coming back out is governed by the fact that the phase space on the outside is much smaller. And so it's just the relative, if you pick, your object that you threw in at some random time and you ask, where is it? Odds are it's going to be inside the black hole. And the chance for it to come back outside the black hole is related to the ratio, the amount of phase space outside the black hole and the amount of phase space inside the black hole, which is all finite when you turn on finite h-bar. So the reason black holes are black in classical physics is that the entropy is being sent to infinity because it goes like 1 over h-bar. The temperature goes to 0. They don't radiate because something falling in sees this infinite phase space, which it sits in and just explores forever. Okay, once you turn on finite h-bar, that entropy is finite, so there's always a finite probability for things coming back out. And so there are no horizons, there's just phase space. And as I was realizing all of this, it reminded me of something that Eric Verlinde tried to make sense of a decade or so ago that he called entropic gravity. That the force of gravity was some kind of an analogy to an entropic force. This is a little bit like that. It's sort of like saying the horizon isn't really a causal horizon. It's just that there's much more phase space over here than there is over here. And so you'd much rather be over here for as long as possible, exploring that phase space. All right. And all of this is also connects smoothly onto the weak coupling picture. So if you ask yourself, you start with this gauge theory on a bunch of DP branes, and you ask yourself, if I make a thermal bound state of the DP branes, what's the likelihood that I can pull one out? Well, in order to be able to do that, to get out onto the Coulomb branch, all of the non-abelian excitations which tie, what are the non-abelian excitations? There are strings that stretch between one D brane that you're trying to get away and the rest of the D branes in the ensemble. So all of those strings, all of the non-abelian pieces of the matrix elements of the gauge theory, all of those things have to de-excite all at once in order for you to escape. And so that's sort of exponentially unlikely at large n. And so this phase space picture is sort of like obvious in the DP brane gauge theory. And the claim is that the calculation that I did sort of exposes that something very similar is happening in the strongly coupled theory, where it looks like geometry. And the role of the horizon in the calculation I did is basically just a proxy for the phase space. The area, that I got the change in the entropy as some kind of tunneling across the horizon. So the fact that I had to have some slightly non-classical trajectory, near the, all of that amplitude came from the piece of the calculation of the trajectory right at the horizon. So the horizon in the classical geometry is just serving as a proxy for that big phase space. So we come back to the question, what is wrong with this picture? And so here I get on my soapbox and start talking about fuzzballs. Because, well, I think everybody would agree not all of this Penrose diagram is appropriate to some physical process, right? The system has a Coulomb branch, so this black brain system couldn't have been there forever. You had to assemble it because if you just, it couldn't have been there from the beginning of time because it would have radiated away all its brains. So you sort of have to assemble it and then watch it decay. And so there's a piece of the Penrose, the past of the Penrose diagram is gone because it's some infalling shell of brains that you make, okay. But then you have this problem that this Hawking process I was describing is some brain pair creation, which is happening over here, whereas the brains that fell in collapsed into some singularity over here. And we fully believe that the gauge theory, even if it's strongly coupled, is doing this, radiating things onto its Coulomb branch in some unitary way. And so if there's to be such a, if the brains are to get out, they can't be sitting over here. They have to be somewhere near the horizon because that's how they're going to tunnel out. And they're not tunneling from here to here. That's no good. because that's an additional non-classical piece of the trajectory. I just looked at a little non-classical piece of the trajectory right at the horizon. Getting the branes from some kind of classical singularity out to the horizon is an additional non-classical trajectory, which would completely destroy the agreement with the thermodynamics. So the branes really have to be right inside the horizon at the moment that they try to escape the system. And that looks more like a fuzzball picture. And any other picture you have of the black hole interior has to explain how, in this context, how the radiation of the branes happens in a unitary way, not where the branes are somehow deep inside in some bag of gold. They really have to be at the horizon. So you know, my favorite resolution of this is that we just get rid of this singularity over here and just replace it by a gas of stuff which is sitting more or less at the horizon scale. And that's basically the fuzzball picture. And so you know, we replace all the black hole interior. We didn't really use any of the black hole interior, right? We just said, I have a brane which is infinitesimally close to the horizon and it escapes. And so I only really used the geometry more or less at the horizon and outside. So what do we need the interior for anyway in this discussion? Because the interior is just the proxy for this huge phase space, not all of which, well, the fuzzball picture is, my picture of the fuzzball paradigm is that the interior is not geometrical. Either it's not there because it's capped off by some bubbling geometry, or in this case, it's really that the interior gets replaced by some kind of brane plasma, which, I mean, it's sort of like n squared plasma degrees of freedom, of which only n to the 0 look geometrical. So why you would call that a geometry, I don't know. And so what I'd like to do is to replace the conventional wisdom with some statement that either there is no interior, or if there is something inside, it's just not geometrical. And then we don't have to talk about how things get from the singularity to somewhere else. So that's basically it. We calculated Hawking radiation of charge from charged black holes. It's a rare event governed by the change in the entropy of the black hole. But if you concoct these situations where that's the only channel by which the black hole can decay, and because, you know, all of the other supergravity modes are in some kind of bound state wave functions, this is the only thing. So it's rare. Okay, just wait long enough and it happens. And so that led us to a picture where what's going on microscopically is just that all the radiation processes are just governed by some generic considerations of ergodicity and phase space volumes. And so in that picture, the horizon is just not a causal barrier. It's just, you know, in the finite H-bar theory, it's just a repository of stuff that can gradually leak out. And thank you.
One quick question. You could probably do this all for, or some version of this calculation in the Penrose process for non-BPS microstate geometry. Can you say something about what that might look like? It's
well, with the caveat that in microstate geometries, you're not accessing all of this phase space at the moment. Right? We're not.
I can measure microstate geometry where I have an effective Ergus surface for.
Oh, yes.
And then I could have it split on one side and partially neutralize the stage.
Yeah. An early version of this was the sorts of calculations that various people, including Samir, did of the J-Mart geometries. Okay, so where yes, so.
I can see the brain. Yeah, so just one brain creation.
Oh, you want brain creation? Yeah, in principle, yes. And stay tuned. Stay tuned. But yes, so to be less glib, so as I was saying, there is a worldsheet formalism for ADS3, and we David and Stefano and I have worldsheet descriptions of JMART, and so the question is, okay, the system is stable in the ADS3 decoupling limit, and the instability only arises when you couple the system back onto flat space. So you imagine there's this very deep 5-brane throat for whose dynamics is going to be governed by the sorts of calculation I was describing, and then somewhere way up the throat, you say, okay, there's flat space, and now these overspinning degrees of freedom can radiate. Well, among the things they can radiate, there's a counterpart of Samir's calculation, was just to ask what is the production rate of wrapped strings instead of particles. But yes, it's very doable.
But you can also do tunneling, I mean, the way we tunnel from one difference into one solution, super, I think that's the same calculation, we get the same reduction. So
yeah.
Let's keep on, I guess.
I don't know where your football went.
And then we'll come back.
Two quick questions, both related to your slide on this eigenstate thermalization thing.
Mm-hmm.
So first of all, I kind of missed how should I think about, because the eigenstate thermalization hypothesis makes explicit reference to, let's say, energy eigenstates, which are pure states.
Yes.
So you said something about I should think about black holes as some linear combination of these pure states. Is that right?
Yeah, I just, where am I? Here we go.
Yeah, this, for example.
Yeah, so I want to think about, to the extent I can think of the black hole and its environment as being separate quantum systems that are, for which there are various transitions going on, like absorption and emission. So, to the extent I can talk about there being a black hole Hilbert space,
right, and
there being a Hilbert space of the environment, then this Hawking emission process is just some set of transition matrix elements
sure.
between those two. And so I sort of, eigenstate thermalization is originally conceived as some process of some closed system,
yeah,
and talking about individual, energy eigenstates. So I'm just sort of like borrowing that language and estimates of, what's a reasonable matrix element for some generic such system, and generic matrix elements of observables, and saying, well, there's some transition matrix element which is mediating these various Hawking emission processes. What could those matrix elements that are coupling the interior and the exterior look like? And I arrived at this picture.
Okay, so a related question is that, is it then possible to compute, let's say, non-Gaussianities of these pseudo-random variables, meaning higher point functions of these curly R's?
I guess that's an interesting question. Before I get there, I should have said this. This calculation I did, where everything is governed by this, the change in the entropy. This is just to get the particle outside the black hole. So then, you have to say, okay, what happens to it after that? So for instance, in these decoupled geometries, if you're not emitting a brane charge onto the Coulomb branch, then you're emitting some Hawking quantum that is, in some supergravity mode, that is in a bound state. So it eventually gets to somewhere and then it falls back into the black hole. So all these subsequent evolution processes that care about what the ambient geometry is and the reflection and transmission probabilities through that ambient geometry, all of that is absent. It would be included in what I did if I calculated the rest of the WKB trajectory outside the horizon and so on. So the first thing that one would want to do is to incorporate in this calculation those sorts of effects. Now, correlations between emissions and so on, that sort of thing, that was part of the reason that Parikh and Wilczek and Krauss were interested in this sort of approach was that they were interested in the question of, for instance, when the emitted quantum makes a big change in the entropy of the black hole, then doesn't the next emitted quantum care about that? And so are there like correlations in the Hawking emissions coming from the fact that, you know, the emissions are not independent because they're all back reacting on the black hole as a sort of an intermediary? And so there were efforts back at that time to compute the sorts of non-Gaussianities you're talking about.
I see.
Using this sort of formalism.
I see. Okay. Thanks.
Thank you very much. I have like a few questions. So the first one is
Not too many.
okay. So two then. So the first one is, does this probability of transition depends on the location of where the string starts to pop out and go to infinity?
I'm not quite sure what you're asking.
No, but like there's like a tending transition, right? From the anti-brain to the brain. That,
yes.
So this brain, so it could be very close to the horizon, and it could be maybe 1 meter away from the horizon. So does the amplitude depend on the distance at which it appears?
Yeah. So in the calculation, the sort of the trajectory that's the least suppressed is the one where I'm analytically continuing the trajectory just in the vicinity of the horizon. So it's following a classical trajectory. You know, just every part of the trajectory away from the horizon. You know, the classical action is real.
Yeah.
And so it's just some phase.
Yeah.
Okay. And so if you try to make the non-classical trajectory longer, it's like I was saying before that
Yeah, I see.
you know, if you try to make it go over 1 meter away from the horizon, then that will be more exponentially suppressed because it's more non-classical over a larger distance, and so the imaginary part of the action is bigger, and so it's more suppressed.
And if I want to think this problem, but in the string perspective, you said that the probability is basically given by the entropy of the bound state. The phase space of the bound state. If I think about the entropy here is like square root of n1 and 5, and can we see that it's also the probability of like this leaking probability would be dependent on the dimension of the intersection between the Higgs and Coulomb branch? Could that be a possibility?
Yeah. So, well, let's see. I'm not quite sure what you're asking. So it's true that I neglected the entropy of the string that's being radiated. So the general version of this calculation is that there's some entropy in the black hole that's left behind, and I could have emitted a string in an excited state. So there's like the general emission probability is phrased in terms of initial and final state entropies, but you have to include the entropy of everything in the final state. So there's the black hole left behind, there's the string, and so there's a okay. So really this S sub F should be, you know, the S of the black hole final plus the entropy of the string that's being radiated. And so, you know, this typically is very small, but you can imagine situations where it's not. So a variant of what I described was analyzed again about 20 years ago in a work by Maldacena, Michelson, and Strominger, where they considered the amplitude for an ADS2 black hole to bifurcate into two smaller ADS2 black holes, partitioning the charges. And this process proceeds by something called the Brill instanton, which is just some ADS2 instanton geometry. And what did they find for the answer? They found that the amplitude for this splitting process to happen is exponentially minus the change in the entropy between the initial state black hole ensemble and the final state black hole. So this result that everything is only depending on phase space just seems to be very universal, applies to many different situations, many different regimes. I think it's something worth following up.
Just want to make one last little comment just about this. A long time ago, when we were completely stuck about trying to make non-BPS microstate geometries, we looked at this system. There was this almost BPS story, but in particular, it was what was called the floating brane ansatz. Yep. And the whole point of that floating brane ansatz was to find some effective Coulomb branch for things which weren't necessarily BPS. Now, they might have been extremal, but there's presumably going to be some set of processes you can calculate for radiation on the Coulomb branch of the almost BPS, well, the floating brane guys. Anyway.
Yeah. So there is something to be said about that. So there is an energy threshold for getting this stuff out onto its Coulomb branch, and so so hidden in this energy term here that's suppressed by the temperature. Is the getting enough radial momentum that you've achieved escape velocity from the non-extremal brane, so the reason I titled the paper "The Polar Wind" is that it's very much like the solar wind or thermal atmospheres of planets, where there's a tail of the Boltzmann distribution where the quanta have enough radial velocity that they can escape the thing that they're gravitationally bound to. And so so as you go extremal, of course, that tail of the distribution is more and more heavily suppressed. And so so there are issues like that. Can you get your floating brane sort of out of the bound state?
When you go extremal, then the force of the barrier becomes smaller. The temperature is less. We can maybe continue this. I think you lose temperature, but you lose also the barrier. So
okay. Well, there's a calculation to be done.
Thanks again, Emil, for this.